Hello, welcome everyone. My name is Yuting Yang and I'm a grad student at Princeton University. I'm going to present our paper, Learning from Shader Program Traces. This is collaboration with Connelly Barnes from Adobe Research and my advisor Adam Finkelstein from Princeton. Shaders are compact programs used to flexibly construct visual appearances and are essential for games, VR, visualization, and other interactive applications. Our paper focuses on procedurally generated fragment shaders, like the ones shown here, which generate color independently per pixel. All of the shaders we use in our experiments are adapted from shadertoy.com. There are also many other great examples on the website. Graphics and vision researchers have investigated a variety of learning tasks for input-output image paths, such as image translation, enhancement, and inpainting. For cases where the input image is generated from the shader programs, researchers have explored a variety of features that can augment simple RGB. For example, when learning shading or Monte Carlo denoising, features from the shading buffers include normal, albedo, and so forth. Such hand-picked features improve the performance of the learned model. In other domains like fluid simulation, additional information such as fluid velocity and vorticity have proven helpful for learning super-resolution fluid flow. Likewise, nerve-based learning methods find that positional encodings are helpful as an extra input to the network. However, these auxiliary features are also manually picked and vary between domains and applications. The main point of this paper is that when learning from a shader program, rather than picking such features by hand, we can allow the learned model to examine the entire trace of the program. The program trace is the sequence of intermediate values computed during execution. Here is an example for the simple shader program sin of x plus y. Its program trace includes each of its intermediate values, shown on the right, x, y, their sum, and then the output of the sine function. Because shader programs generate 2D images, we can also think of its trace as a series of 2D feature maps, or 3D tensor. This is a much more complicated program called TriviHeart. Its program trace contains features progressively generates the psychedelic appearance, as well as the mask and the shape of the heart. Here we are only showing 5 examples of trace entries, but there are actually hundreds of them. Returning to the learning problem, typical network architectures take a 3-channel input tensor encoding in RGB. The point of our paper is that the model can learn instead from an n-channel input tensor that includes not just RGB and not just a few hand-picked features, but rather the full program trace. We propose several applications that could benefit from this method. The first is learning to reconstruct a denoise image like the one on the right from the noisy input image shown on the left, which can be computed more quickly because it only uses 1 sample per pixel. Our second example is reconstructing the original denoise shader rendering shown on the right from the output of a simplified program shown on the left. The simplified program runs much more quickly, but notice on the left, all the high-frequency textures are missing. Our third application, post-processing, can be thought of as an add-on to the previous 2 applications. We further apply a post-processing filter to the rendering. For example, here we learn both denoising and the local Laplacian filter at the same time. Our last application is a simulation of flocks of birds, which emulates the bird's flocking behavior. Our model learns from the trace that runs the simulation for 1 step and predicts future state as if the simulation were executed for many steps. Program traces has been used in machine learning applications such as malware detection or program synthesis. Similarly, partial rendering has also proven useful in inferring parameters for procedural models. Unlike application-specific designs, This paper focuses on a generic method that learns from shader program traces, which enjoys certain unique properties such as an emphasis on pixel outputs and an enormous degree of parallelism. We now start to describe details of our proposed framework that learns from program traces. Our compiler takes as input an arbitrary procedural shader program written in a domain-specific language embedded in Python, and outputs to a TensorFlow backend that produces not only a rendered image, but also the full program trace, which is a vector of values per pixel. On the left is an example that generates the striping pattern in our DSL, and on the right is the compiler-generated TensorFlow program that also collects the intermediate values in the program trace. Because each trace has a spatial size that's the same as the output, the computation is embarrassingly parallel and needs minimum modification for downstream deep learning models. However, the proposed method is not as straightforward as directly feeding concatenated program trace into arbitrary network. There are two challenges that I'd like to discuss today. Firstly, program traces can be arbitrarily long, which introduces learning difficulty both in terms of memory footprint and in runtime. The first technique we handle is trace optimization. Instead of naively logging every program trace entry, our compiler already performs some optimization to get rid of highly correlated traces, such as ones differ by a constant factor. The compiler also identifies common built-in functions and logs only function output. Built-in functions are usually ones we wish to treat as a black box, such as sign. Finally, the compiler also identifies iterative improvement loops and logs only the trace from the last iteration. This is because they repeatedly improve an approximation result to obtain a more accurate result, such as a rate marching loop, and only the last iteration is the most informative. The approach I described so far helps, but only to a limited extent. Therefore, we introduce a more general feature subsampling strategy. The most straightforward way is to log every case intermediate variable. Here, we are showing the entire program's computation as small cells, where only blue cells are logged. Also, because loops usually create a large number of program trace entries, we explore the variety of subsampling rules specific to loop iterations, such as loop subsampling that logs every case iteration, or logging last and first k-loops, or other strategies such as collecting mean and variance across loop iterations, or clustering program trace entries based on their correlations. Empirically, we find that the general uniform subsampling always works good enough. This coincides with the no free lunch theorem, which suggests that without prior knowledge, there is no single choice that could outperform all others on every aspect of the evaluation. Additionally, because generating a high-quality ground truth denoise result at 1,000 samples per pixel can be expensive, our learning task is limited to a relatively small dataset. For efficient learning, we note that each ground truth denoise result is paired with a 1 sample per pixel noisy input during the training process. So, during training, we can efficiently re-render the noisy 1 sample per pixel input by drawing different samples within the same pixel, which still corresponds to the same output. Therefore, although our output ground truth data is limited, we actually have infinitely many input-output pairs. For example here, the noisy shader rendering could have multiple different copies with slightly different random offset on each pixel, but they all share the same ground truth image. Our method is actually orthogonal to the design of network architecture or loss metric. This is an example network we used. We also experimented with a number of other designs, and they are described in our paper. To evaluate our performance, we introduced several baselines. The most naive baseline is RGB, which simply uses the image input. The RGBX baseline is motivated by the hand-picked auxiliary features used in denoising Monte Carlo sequences. We find that the RGBX baseline always outperforms RGB, so we report only the RGBX whenever possible. We additionally include the supersampling baseline for denoising application only. Samples are chosen to have comparable runtime with the neural network inference time. This is the visualization for our quantitative comparison. The bar shows relative LPIP's perceptual error compared to the RGBX baseline, which is indicated as the blue line above all bars. It is quite straightforward to see that all of our experiments have smaller error than the baseline. Now we show qualitative results on different applications, starting with denoising. This is the oceanic shader we showed before, where we trained the denoising model to predict rendering generated at 1,000 samples per pixel. We first run the shader at 1 sample per pixel and then denoise the result. We can compare on a still frame by zooming to the highlighted region. Ours better recovers the wave detail in the foreground. Here we show a Mandelbrot shader. This is the ground truth estimated at 1,000 samples per pixel. The RGBX baseline removes most of the noise, but some of the thin structure is broken, such as the region in the highlighted circle. Here is our result that nicely reconstructs the thin structure. We can take a closer look to the zoomed-in region. Ours reconstructs the thin structure nicely, while RGBX demonstrates artifacts. We now present results for simplified reconstruction. Here we show the ground truth image for Venice shader with high number of remarching iterations that nicely builds the scene. A simplified shader uses less number of iterations than the original one. Therefore, the streetlights and the sidewalks far away have significant artifacts. Our method learns to extrapolate the more complex shader rendering from the program trace of the simplified shader. Note we have recovered the distant views. Let's take a closer look. Ours better reconstructs the distant buildings, while RGBX has a transparent artifact. This is another example of bricks. The ground truth is the denoise rendering of a more complicated shader, where each tile has random color variations generated by simplex noise. The simplified shader lacks the detailed color variation on each brick tile. Our method recovers the color variation naturally. Let's look at the zoomed-in region. The simplified shader lacks the color variation on the bricks tile. The RGBX baseline tries to generate the pattern, but is inconsistent with the ground truth. Ours, on the other hand, faithfully follows the ground truth. We will skip the post-processing application as they share similar properties as the denoising and the simplified application. And we now demonstrate an example on simulation for flux of voids. This is the reference. The position and velocity between each frame are updated by 20 simulation passes. Because of the fine-scale simulation steps, the voice accurately emulates the flocking behavior of birds. This is a naive baseline, where the state between frames is updated by only one simulation pass with a larger step. We can clearly see that because this baseline takes a large step without any correction to the voice positions, the voice behavior doesn't make sense at all. This input-output baseline is an analogy to RGBX. We take one simulation step as input to the learner and learns to extrapolate to the larger step. We can see that the learner extracts some behavior, such as not to hit walls and to avoid neighbors in some extent, but the alignment is still quite poor. Our method correctly reconstructs all the flocking behavior, and even learns the bumpy repulsion when the boy is trying to avoid all of its neighbors, as well as the wall. We analyzed which traces are more important using existing metric for Monochov 2019. We find the important traces corresponds to human intuition. For example, for bricks shader, important features include distance to the nearest brick edge, and the boolean that indicates whether the pixel is inside the mortar. This can help prevent the edge from being broken. We also analyzed which subset of the program trace best benefits the learning task under a fixed budget to the number of input program trace. By default, we use uniform subsampling, which always works well. Another strategy is to emulate all possible trace combinations and train a separate model for each of them. However, this introduces a combinatoric number of learning tasks and is intractable. Therefore, we propose two subsample strategies based on the importance score, both relying on training an additional model on every program trace. We can use the trait model to choose a subset of the trace with the highest importance score, which we call oracle subsampling. Similarly, we can also deliberately choose the traces with lowest importance score, which we call opponent subsampling. Here we compare the three different subsample strategies using Mandelbrot shader. Uniform is the one we use in our main results. Opponent is always worse than uniform because it chooses the worst features, and oracle is always better than uniform because it chooses the best features. But both oracle and opponent requires training an additional model with the full trace. Here's another example for Mandelbrot. Note there's a large performance gain by using extra program traces. For trippy, we can pick a short trace length, and uniform subsampling is often as good as the oracle. Note even when the sample budget is small, we can pick a short trace length corresponding to the left parts of these plots, and the extra information from the program trace can still substantially reduce the error without significant extra cost and inference time. Here are some discussions we feel might help future exploration in this direction. Firstly, besides training a model per shader, we could also explore whether part of the learning model can be shared across shaders within the same task. In our paper, we included a preliminary result by training a shared denoiser for 4 shaders. Ours can still outperform RGBX with 60% perceptual error on average. Our current framework also has some limitations, which leads to future work. For example, because the neural network's inference time is not negligible, the proposed framework may not be practical for simple and fast shaders, as they could easily use the time budget to draw more samples. Future research might address this by developing specialized networks that are more efficient for inference. Additionally, the TensorFlow backend may become a bottleneck for some shaders, such as complex BRDFs, or branching generated by varying number of rate bounces per pixel. We believe further engineering efforts may alleviate these bottlenecks, such as adding a GLSL frontend prior to the inference process. In conclusion, we present a compiler framework to augment neural network input with shader program traces. Our method consistently outperforms baselines such as RGBX, which uses manually picked auxiliary features as model input. Our analysis further shows that even subsampling a small subset of the trace can already improve performance against the baselines. With this, I will conclude my talk. Thanks everyone for coming. I look forward to discussing with you in the live session.